All right, so now let's go on to example 2 in your lecture guide. I'm on page 10. The function p of n equals x cubed minus 19.5n squared plus 102.5n plus 16 gives the profit a company earns, where n is the thousands of employees working on that day nationwide, and p of n is the profit in millions of dollars at that particular day. The company is only capable of employing at most 13,000 employees on any given day, and the graph below is displaying this. So I'm going to go a little bit out of order of the guide on the lecture guide, and because you know me, I always like to label my axes first. So I'm going to do part B first. We're going to say, okay, let's label each axis first with the real world meaning of each axis, the variable on each axis, and the scale on each axis, or in other words, what's its units, and look at the scale. So let's see here. Let's look again. P of n is implying that n, the inside the parentheses, is my input variable. P is outside the parentheses, implying my output variable. So my input variable is n, and we look again, n is representing thousands of employees working on that day. So n is my number of employees in thousands. Now, why is my scale in thousands here? Because I see my tick marks here. I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? As we go here, 1, 2, as we go to 13. We have 13,000 employees, so our units are in thousands. And then P of n is my output variable, where they said P is equal to the profit that the company earns in millions of dollars that day. So P of n is profit in millions of dollars. All right, so now we've labeled our axis. Let's put our scale in here. We said that this was 1 through 13 because we're talking in thousands of employees. And this is from negative 50 to positive 250, but it's in millions of dollars per day. Okay, part A goes back and says, what's the practical real-world domain in this problem? Write your answer in interval notation. Well, our domain here is the number of employees. And in real-world practical terms here, we're talking about from 0 employees to 13,000 employees. So my domain in interval notation would be from bracket 0, comma 13, or set notation would look something like this. And in a real-world practical terms, writing it in a sentence, we would say the number of employees working on any given day, we were told, is between 0 and 13,000 employees. Okay, let's go on to part C. Part C says, estimate the local maximum point. Okay, now let's see, what is a local maximum point? A local maximum point is the point on the curve that is higher than the points around it in a local vicinity. There's actually 2 values here. Over here at the very top, we actually have the absolute maximum value here, which again, remember, is also a local maximum. But we also have this other point on the curve right there, which is another local maximum point. So I'm just going to estimate that. My local maximum point is estimated to be at the point 4, about 4, and I'm saying about 175. Again, I'm just estimating it from the curve. And another absolute maximum, which is also a local maximum, here at 13,250. So let's put it into a sentence, as we like to put it into context. So that means when 4,000 employees are working on a given day, the profit reaches a local maximum of $175 million. Or when 13,000 employees are working on a given day, I reach my maximum, absolute maximum profit of $250 million. Part D asks when the function is decreasing at the fastest rate. And what is that point called? Well, first, let's talk about where the function is decreasing. The function is decreasing when the curve is falling from left to right. So we say that the curve is decreasing in this interval from about 4, which was that local max, to about, what do we say, 9.5 or so? So this is where the curve is decreasing. But it's asking, where is it decreasing the fastest? In other words, where is it the steepest? Where is it getting the steepest rate of change there? The inflection point, the point of inflection, actually is the point where the function will increase or decrease at the fastest rate. In other words, it will be falling or has the steepest slope in the negative or positive direction here. In this case, negative direction. So this curve is going down the fastest, at the fastest rate, at about 7. A little bit, actually probably more closer to 6.5, but pretty in that ballpark. I guessed around 7/130 is the actual point on the curve. This locates the point of inflection. This is where the concavity of the curve is changing, where the curve is changing from being concave up to concave down. So when 7,000 employees are working on a given day, the profit is $130 million. At this point, the profit is decreasing at the fastest rate. Now, if we talk about concavity here and rate of change here, notice when the curve is concave down, but the curve is rising, we say that the curve is increasing, but the curve is slowing down that rate of each increase. In other words, it's over here, it's going up really fast, but then notice it's curving downwards. So we say, okay, it's increasing but less, increasing but less, increasing but less, until it reaches its maximum. So we say it's increasing, but it's kind of slowing down at a slower and slower rate until it reaches its maximum value. Then I start decreasing, and I'm decreasing more until I get to that point of inflection. So I'm decreasing at a fast rate until I get to the fastest rate of increase at the point of rate of decrease at the point of inflection. And then I continue to decrease, but it's now changing concavity. So I'm slowing down my decrease. So I'm slowing down, but not as much. I'm going down, not as much, going down, not as much, until I reach my minimum point here. And then I'm increasing at a faster and faster rate. Part E says, identify the interval where the function is increasing, and then write a complete sentence to interpret the real-world practical meaning of this answer. So let's go back to what we were saying before. We say that the curve increases when the curve rises as we move from left to right. So we said on the interval from 0 to 4, this function will increase. And then on the interval from 9.5, right about here, 9.5-ish, to 13. On these intervals, in this interval right here, the curve is rising, therefore the function is increasing. Here the curve is rising, therefore the function is increasing on these domains. Remember, these are not ordered pairs. These are on the domain interval from 0 to 4 and from 9.5 to 13. So let's write a sentence here. We would say, as the number of employees increases from 0 to 4,000 and from 9,500 to 13,000, the profit is also increasing. Part F. Identify the intervals where the function is increasing and concave down at the same time. Okay, let's think about this. And then write a complete sentence to interpret what does this mean in the practical terms, in the real world. So we already talked about where the curve is rising or increasing. We said from 0 to 4 and from 9.5 to 13. But not only does the curve have to be increasing, but it also has to be concave down. So let's look in those two regions from 0 to 4, the curve was rising, increasing, and also concave down. So that checks off both of those boxes. Let's look at the other interval from 9.5 to 13, the curve was also increasing, but it was not concave down. Notice the bend of the curve over here is bending upward, therefore not concave down. So the only interval that this curve is increasing and concave down is on the interval from 0 to 4. So as the number of employees increase from 0 to 4,000, the profit is increasing, but being concave down, it is increasing at a slower and slower rate. So over here, the rate, you can see the curve is rising pretty fast. It's pretty steep over here. But then the curve is increasing, but not by that much every time as we move closer and closer to 4. Let's look at example 3. The population of the town is given by this exponential equation where t is in the number of years since 1950 and p of t is the population of the town in thousands. Again, let's label our axes with real-world meaning of each axis. What do they mean? Let's look at the function notation. This always gives us a clue. The inside function, the inside variable inside the parentheses gives us our input variable of t. That always goes along our horizontal axis. And they said t was the number of years after 1950. So this is my label and my units here for my horizontal axis. My output axis is p of t, which they said stood for population of the town, and its units was in thousands. So this is population of the town in thousands of people. Part B says, is the function increasing or decreasing? And what is the practical real-world interpretation of this? Well, we can definitely see that the curve, it is an exponentially decaying function, which we were definitely clued into here because we know that the factor is less than 1. So we knew that we were going to have an exponential decay here. So this is definitely a decreasing function. This function is decreasing. And what is it telling us? It's telling me as the number of years increase since 1950, the population of the town is also decreasing. Or is decreasing. So as time moves on since 1950, the population of this time of this town is decreasing. Now, because the curve is concave up or down, let's look, that's question C. Is this function concave up or down? This function is concave up. So what do we notice? Over here, the curve, the population is dropping pretty fast. But then as time goes by, the output is not dropping so fast. It's not, the y values are not dropping so fast here. So we say this curve is concave up. This means that as the years increase from 1950, the population of the town is decreasing, but it is decreasing at a slower and slower rate as we move. Part D, identify the right tail function behavior of this function and write a complete sentence. All right, so let's look at our right tail behavior here. What's true about our right tail behavior? As this population gets, as the time gets closer and closer to 70 years after 1950 here, right? The population of the town is getting closer and closer to 0. So we would say that our right tail end behavior here, as the number of years increase from 1950, the output or the population is tending towards 0 here. So the output of the function approaches 0 as the input increases. So let's put it in context using population and time. So we say by the year 2020, which is 1950 plus the 70 years that we're talking about here, the population of this town will approach near 0. We're almost having a ghost town after all these years.